Hello and welcome to our program, Astronomy for Everyone. This month's show is actually our 4th anniversary on the air, and we want to thank our viewers for their continued support. Our topic for the show this month is the Curiosity mission to Mars. And while Curiosity has been on Mars only 6 months and traveled less than half a mile, it has already gathered enough information to tell an interesting story, including evidence that Gale Crater, its landing site, was once wet. Curiosity carries the most advanced payload of scientific instruments ever used on Mars. And here to tell us about it is our own Astronomy for Everyone team member, Steve Whitty. Steve, what's the word on Curiosity?
Curiosity landed on Mars. It was an exciting and it was a great landing, and the rover has been checked out over the last 6 months. Most of the things that it has done has been the engineering team, not the science team, the engineering team checking out each of the cameras, checking out the chemical instruments, the drill, the Mars dial, which we'll get to. All of these things got checked out, and basically everything works. It's a fabulous rover. It's a fabulous mission. So what we have here is a remote control geologist right on Mars. I'd like to read, because I can't remember it verbatim, I'd like to read the mission statement. This is NASA's mission statement for Curiosity. Curiosity's mission is to determine whether the red planet was ever or is habitable to microbial life. Right? So things that microbial life needs on Earth include water, and the site, Gale Crater, was with Mount Sharp, was chosen because from orbit it looked like a really good spot to land. And what Curiosity has found without any doubt is that this was a great place to land the Curiosity rover for the investigations that it needs to do.
Because of the conditions, as you mentioned, they're looking for water and other things that were conducive to microbial life.
That's right. And the instrument package is designed to figure out the geology and therefore the history of Mars, of this section of Mars. And this site gives you layered history clues to work with. And even in the first 6 months, for a multi-year mission, the rover has already seen some extremely exciting geology, and has already determined that, yeah, this was the right place to land.
And so we're going to take a look at some of these scientific instruments that are aboard Curiosity. Which one do you want to start with first?
Well, let's start with the rover itself.
Okay.
So before the rover was on Mars, it was at JPL in Pasadena, California, and here it is. It's doing a turn in place. So it has 6 wheels, and the wheels can each be turned independently, and the thing can rotate, not just like in a turning radius with a car, but it can rotate with the center of the rover really not moving. The wheels are pretty big. The whole unit is the size of a small SUV. It's it's
the biggest one we've ever had on Mars.
It's certainly the biggest one we've had on Mars, and it was and it has the most stuff. It's by far the heaviest thing that we've put on Mars as well. So we figured out where to land by using orbital images from the
that was the Mars orbiter?
The Mars orbiter. So here's an image which shows the first tracks, maybe the first 50 yards. And you can see the rover on the right, the bright object on the right. On the left there in the blue spots, that's where Curiosity landed on Mars. And you can see the tracks that lead from the landing spot to where it was by the end of this, by this image. So this is a very curious shot. In previous rovers and in previous instruments, or landers, it was difficult to really get a feeling for what the rover looked like in where it is. This is a self-portrait using the MOLLE, the hand lens imager, and it took maybe 50 or 60 shots, which were then stitched together to make this image. So the images are actually from different angles and different places. You don't see the mast on the rover because that basically has been edited out by placing other images that happen to have background objects.
So this is Curiosity's self-portrait.
This is Curiosity's self-portrait. Curiosity has done this more than once, and it's an interesting image. It really gives you the feeling, oh, this is Curiosity, and this is where it is. You can see off to the right in the background, you can see Mount Sharp, which is the mountain that Curiosity is going to eventually climb. So it's going to see the layers as it's climbing. So again, from orbit, we can see where Curiosity rover has gone past a spot they called Jake Majedovic. This is really tough.
Jake M.
Majedovic.
There we go.
There we go. And then on to Rocknest, where it spent and did a number of interesting operations. And then you can see that it has gone off to the right. There's it's labeled rover almost at the right edge of the screen, and the little bright spot there. It has been going mostly downhill since then. So
literally, not figuratively.
Literally, yeah.
Yes.
And it's not that far. You know, they call it 20 meters. I think of it as 20 yards vertically down. But in the distance that it's traveled, it hasn't been very steep.
Okay.
The engineers who put together the Mars rover, when they were picking a landing place, the scientists were saying, oh, this place is going to be really tough. It's really steep. And the engineer says, no, it's designed for steeper than that. That's still an option. So in an interesting way, the engineers were the ones that were saying, no, this rover can do it, and the scientists were being very cautious. That's not the usual way it works. So we could get back to SAM.
Okay.
SAM is the set of it's the sample analysis package. It has a bunch of sub-packages which are individual instruments, and these instruments they can analyze materials. They can do it spectrographically. They can shine X-rays through it to find out crystallography. They can there are a bunch of analyses that they can do, and they can really characterize what it is that they're working with, what the elements are, and what the mineralogy is.
So, as you said, the geologists are having a field day with this.
Absolutely, absolutely.
Well, what about we've got dust removal?
That's coming in our next segment, I think.
Okay.
Or is it? What is our next? Oh, so this is sort of a breakdown of. There's a drilling apparatus, and there are a bunch of things that happen. So the rover can drill a hole, and it can extract material from the hole. It then can sift the material that it has so that it can get the right grain size, because it's very important for these instruments to have the right grain size, otherwise they won't work properly, or
They're looking for a uniformity of grain size in the sample?
It's not just the uniformity. They're actually looking for a grain size that the analysis instruments are designed to work with.
Ah, okay.
And so it's hard to see from this image, but the material actually flows around quite a bit before it finally goes into the SAM instruments for analysis. Can we move on? All right, so here's Mount Sharp from, I believe, the hand lens. There's a hand lens on the end of the mast cam. I mentioned it earlier. And it's not just able to take pictures that are close up, it can also take pictures that are far away, so it has focus control. And this is Mount Sharp just as a sort of a close-up.
Those are some great images of Mount Sharp, Steve. We're going to go to our break right now. If you would like some more information, you can visit our website. You can see it down there at the bottom of your screen. And coming up next is Term of the Month, so don't go away.
The term of the month for May 2013 is sand. This is sand from the perspective of curiosity, which is a geologist. A guy by the name of Wentworth described sand in a paper in 1922, and he talked about gravel, sand, silt, and mud, and these are by the size of the grains. Now, sand comes from, in size, from about 2 millimeters to about 1/16 of a millimeter. So this is a 1/2 millimeter pencil, and so the lead in the pencil is a 1/2 millimeter in diameter. So that's one of the size boundaries. In the chart, you can see that there's fine sand, coarse sand, very coarse sand, fine sand, and so on. And they go from large to small. So from 2 millimeters to 1/2 millimeters, that's the pencil, you have coarse and very coarse sand. And then you have fine sand below. So it's like 60 microns and at the very bottom. And the way to think about that really is 1/16 of a millimeter rather than in microns. I have a hard time thinking in microns. Now he has gravel and other things above and below. We're not going to go into that. These triangles have sand and silt and clay at the corners, and then you have salty sand and you have sandy salt or sandy silt at the interfaces. And these sort of ternary diagrams give you an idea of the mix of the minerals. Anyway, that's a brief overview of sand, term of the month for May 2013.
Welcome back to our program. This month's topic is on the Curiosity mission to Mars. And with me here in the studio is our own Stephen Whitty. Stephen, dust removal. What do we know about that?
Okay, so we've got this wire brush tool right on the arm. So the arm comes from the top of the rover and can go down onto the ground. And it's really just a wire brush. It spins. And so here are the results. You've got the dust has been removed, and you can see that the material on the ground, the rock that you've got there, is different. It's a different color, and it's a different sort of material. And that means that the dust that's everywhere is being blown around in the thin Martian atmosphere. So the material that is the dust isn't the same material as we're seeing in the rock.
So we don't see that ferrous oxide in the rock that we see in the soil making it red?
Absolutely not. So it's just a completely different sort of animal, or in this case, mineral.
There you go.
So we have this drill facility. Again, it's on this on the arm. So the drill can be reached out and be placed on a rock. The drill is a little over 1/2 inch in diameter. The drill hole is then goes maybe 4 inches deep. A sample is taken, and the sample isn't taken from the bottom. It's taken from about 2.5 inches down, and then most of the sample is removed. There's also a scoop, and the scoop can just basically scoop up some of that dust, some of that loose stuff. The scoop is fairly narrow. It's only a couple inches wide. It's very much like a scoop that you'd find in your kitchen. It's not huge. So this is what the dust looks like that has been drilled from the drill. And it's by the time you see it here in this scoop, it has gone through a number of processes. It has been spun, it has been shaken, sort of sifted so that you get a consistent but fairly fine grain, what are we going to call it? We're going to call it a dust or a soil, if you will. But it needs, the grain size needs to be a particular size because the analysis instruments, and that's the X-ray spectrometer, the chemin, the chemical analysis instrument, and so on. These instruments are designed for a very specific grain size.
This way they can have good results, repeatable results, and not have them skewed by random size particles?
That and also the material has to flow through a really complicated set of tubes and stuff to get into these instruments, and we don't want it clogging. One of the big fears that the scientists and engineers alike have on this mission is that somehow a sample will be wet. Now, Mars doesn't have a lot of water. It is drier than the Sahara Desert. It is drier than almost any place on Earth. The Atacama Desert in Chile is often touted as the driest place on Earth. Mars is drier. But Mars does have water. In fact, we've even seen it rain, not by Curiosity, but by previous missions. So the water isn't a high likelihood, but it could potentially really gum up the works.
It wouldn't be flowing as a fine powder. It would.
It could just clog everything.
Oh boy!
Yeah.
You can't call a service technician to go out and shake it loose.
It's quite a ways away.
Okay.
Yeah, even at light speed, it can be 20 minutes.
So the image we have up here now, what's?
So yeah, all right. So the X-ray spectrometer is looking at the crystal structure of the material. So we've ground it up. It goes into this thing. X-rays are shot at it, and the X-rays deflect at random angles. They seem like random angles away from straight on. And so you see circles around it, and each of these circles, each of these brighter circles corresponds to an expected grain size or grain or mineralogy. And so you can say, oh, we have some gypsum here, and we have
some quartz or whatever.
Yeah, et cetera. So you can tell by each line what it is that we're seeing, and a number of minerals have been identified already.
What about the Mars dial?
Okay, so the Mars dial is kind of interesting. On the one hand, it is a sundial, right? So the Mars day is a little longer than an Earth day. It's about 25 hours. It's not quite exactly 25 hours, but when you're working on Mars, you work on Mars time, not on Earth time. So you have a little bit longer day when you're working in California and sending commands out. But it's not just a sundial. It's also a target to calibrate the color images. If you've got a color image, you want to know whether the red that you've got is pink or more reddish.
Balancing the RGB on it?
Exactly.
Okay.
You need to do that. And you'd think, oh, well, you would just do that on Earth before you launch. But what happens is that dust coats everything, and that includes the lenses of the cameras. And what can happen is that the color can actually shift a little bit just because...
That dust throws off the calibration that you set here on Earth.
And then also the Mars dial itself gets dusty, and you kind of want to calibrate the dust that is on the objects that you're looking at. So it has a number of sort of subtle features to it, and it looks just like it's a stick with,
Looks like a joystick, eh?
It really does look like a joystick. I could play my Atari. That would be a half-ton Atari that you'd be working there. Okay, so one of the things that we discovered just after we landed was a little bright thing near the lander.
A bright thing is a technical term, by the way?
It's a highly technical term.
Okay.
And it was determined to be a piece of the lander itself. It was a little piece of plastic that was... but that's not what this is. This image is a piece of real Mars. And it's a little bit of rock sticking up. And the first thing that you think of is, why is it so bright and everything else is covered in dust and it's not? And one of the reasons is that it sticks up, and the wind is sort of sandblasting it, and it has sandblasted it so that you're looking at the underlying stuff,
Have they determined what this material is?
I don't think that this this object has warranted close scrutiny. I think they said, yeah, we know what kind of a process creates this sort of a bright thing. We were initially worried that it was a piece of the rover itself. We determined that it wasn't, and otherwise we decided it wasn't as interesting as other things that that we were much more interested in. This image is taken by the hand lens imager, the Mali again, but it was taken at night, and taking it at night does something interesting that you can't do during the day, which is at night you have total control over how you illuminate the object that you're taking a picture of. So there are 3 or 5, I think it's 3 white light LEDs, and they can be positioned from various angles, and so you can see what the shadows look like, but you can also make sure that you get the light coming from the direction that you want it, so that you get reflections that that will show the contrast that you're interested in. So I think the idea of shooting pictures at night is an interesting one. I might not have thought of it. 2 things make that possible. One is that this rover doesn't have solar cells on it for power. It has, you can call it a nuclear power source. There's a radioactive material. It gives off heat, and the heat is turned into electricity, and that powers the rover. It keeps it warm, and it gives it electricity.
So they don't have the problem of dust landing on the solar panels and reducing its energy.
That's right. That's right. It's a 2-year mission, but the power source should last way longer than that, perhaps 10 years or more, maybe 20.
Let's hope so. I mean, we've got the Cassini mission is still going strong, and it was only supposed to go 3 years. So.
And we have the Voyager missions that have been going for 35.
So here's hoping it does last. I want to thank Steve for taking time out to be with us today to talk about the Mars Curiosity mission. If you have any questions, please send us an email. You can see that down at the bottom of your screen. We'd love to hear from you. And right after this, we have What's Up?
What's up for May 2013? We've got some interesting things here. We're going to start off with the moons. On May 2nd, we have the 3rd quarter moon. We start off the month, 3rd quarter, it's a Thursday. So it's more or less end of the week that you have the changes of the moon. On the 9th, which is also a Thursday, we have the new moon. And there's not much to see on the new moon. You know, it's basically where the sun is. On the 18th, we have the 1st quarter. This is a Saturday. The 3rd quarter is visible, you know, from noon to like midnight. It's an evening sort of object. On the 25th, we have a full moon, and it's up all night long. And then on the 31st, we have a 3rd quarter moon again, and it's on a Friday. So the day of the week has shifted a little bit. If this was a full moon, this would be sort of the blue 3rd quarter. Well, that's not how we talk about it. Next up is the planets, and this is a view on the 11th of the month. Down at the bottom we have Venus, so Venus is making a show this month, and then On the 11th, we have the moon. It's in the middle, and the moon will be, it's just a couple days after new, so this is a very thin crescent moon, but it should be enough to sort of guide you to the general area. And then above the moon, we have Jupiter. Jupiter, we pretty much lose by the end of the month, but Jupiter is a spectacular planet, even if it's fairly low to the horizon. Also on the 11th, this is an image of Saturn, and Saturn rises in the east, so this is like an 8 p.m. image, and you can see it most of the night. We're just past opposition where it's up all night long. So it sets maybe at 4 a.m. At the earliest all month long. At the end of the month, this is at the very end of the month, Mercury is still pretty low to the horizon. It sets at almost 10 o'clock. I mean, it's a quarter of 10. Venus, you can see, is below it, and Jupiter is below that. So Mercury is tough to see. Generally speaking, it's worthwhile looking for it if you've got a good western horizon. This astronomy software doesn't simulate a great western horizon. Here you can see that the planets are in the trees. Yeah, that's Mercury, Venus, and Jupiter. In May, on the peaking around the 4th and the 5th, are the Eta Aquarids. This is a meteor shower, and of course, astronomers come clean with a meteor shower. Now, around the 4th and 5th, we have a third quarter moon, and the moon rises at 2:30 in the morning. So the shower is best after midnight, but once the moon is up, it can really make it difficult to see the fainter meteors. So your best bet is really midnight to 2:30, but you'll be able to see meteors in the evening as long as it's dark. Next up is the month's constellation, Canis Venatici. And Canis Venatici has a number of interesting things. It has, it's called the hunting dogs. It's located sort of under the arm, if you will, of the Big Dipper, the handle of the Big Dipper. The stars in it are not that bright, but there are really only two that are there at all, and it has a wealth of objects in it. And that's that's what's up for May 2013. The night sky is the greatest free show on Earth.